Hi! In this lesson we are going to study the operation of modular exponentiation. This operation is central for public key cryptography that we're going to study in the next module. Its properties allow for fast encryption and decryption for Alice and Bob, and it is easy for them in one direction, but it is hard to reverse for Eve, who doesn't know something that either Alice or Bob knows. So first we're going to study how to compute this modular exponent quickly in this video, and then in the next videos we're going to study the key properties that make it useful for encryption and decryption. So modular exponentiation is the operation of computing b to the power of e modulo m. So we need to compute number c, which is equal to b to the power of e modulo m. And how to do that? Well, there is no need to actually compute the possibly giant number b to the power of e and then divide it by m to get the remainder. Instead, we can just start with 1 and then multiply this number, which is at first 1, by b, immediately take the result modulo m, then multiply the result by b, and again take the result modulo m, and so on, and repeat all this e times, and we will get the remainder of b to the power of e modulo m because of the properties of remainders. Basically, the remainder of product is equal to the product of remainders, and this is the main property we are using here. So, for example, if b is equal to 7, e is equal to 4, m is equal to 11, basically we need to compute b to the power of 4 modulo 11, and we start with assigning value of 1 to c, and then we want to 4 times multiply this c by 7 and take modulo 11. So first we get 1 times c, which is equal to 7, and it has a remainder of 7 modulo 11. In the next step, c already has value of 7. We multiply 7 by 7, get 49. 49 is 44 plus 5. 11 divides 44, so the remainder is 5. On the next step, c has value of 5. We multiply 5 by 7, get 35. It is 33 plus 2, so the remainder is 2. And finally, the c already contains value of 2. We multiplied it once more by 7, we get 14, and the remainder modulo 11 is 3. And finally, we conclude that b to the power of e modulo m, which is 7 to the power of 4 modulo 11, is equal to 3. So this is the basically straightforward algorithm to compute modular exponentiation. We just start with assigning 1 to value of c, and then we repeat e times c is equal to c times b modulo m. And that's the whole algorithm. So we need just e multiplications, and that's fast enough, right? Well, not always. What if b, e, and m are actually integers with thousands of digits? And this is actually a practical case for cryptography. We need to work with really large integers so that Eve cannot decipher our messages. If b, e, and m are very small, then it would be very easy for Eve to decipher. But if we want our algorithm to work, then these numbers must be very big, and then making e multiplications where e is a number with 1000 digits, well, it won't finish in our life or probably in the time of existence of this universe, so we have to come up with something much faster than e multiplications. So can we actually do faster? Well, let's first consider the case when e is a power of 2. E is equal to 2 to the power of k. What we can do then? Well, on this example, when b is again equal to 7, but e is equal to 128, which is 2 to the power of 7, let's see what we can do. So first we can compute 7 to the power of 1, which is just 7, and then we can proceed with what is called squaring. So instead of computing powers of 7 as second power, third power, fourth power, and so on, we're going to square each time. So first we compute 7 squared, which is equal to 7 times 7, which is 49, and modulo 11 is equal to 5. Then, given that 7 squared is equal to 5 modulo 11, we're going to compute 7 to the power of 4 as product of 7 squared times 7 squared, or square of 7 squared. It is equal to 5 times 5, which is equal to 25, which is equal to 3 modulo 11. And on the next step, we're going to compute 7 to the power of 8, given 7 to the power of 4 equal to 3. So we are going to square this 7 to the power of 4, get 3 times 3, which is equal to 9 modulo 11, which is just 9. And again, we're going to compute 7 to the power of 16 by squaring 9 and get 4. Compute 7 to the 32 by squaring 4 and get 5. Then 7 to the 64 by squaring 5 and get 3. And then finally 7 to the 128 by squaring 3 and getting 9. So actually we made just 7 multiplications to compute 7 to the power of 128 instead of 128 multiplications. That's significant improvement. And in the general case, the algorithm looks like following. We start with assigning value of b modulo m to c, and then we repeat k times c assigned to c squared modulo m. And in the end, this c will be equal to b to the power of 2 to the power of k, which is equal to b to the power of e modulo m if e is in the form of 2 to the power of k. So instead of e multiplications, in this case we need just k, which is equal to binary logarithm of e multiplication, which is much faster with large E. For example, if e contains 1000 digits, then k will be just on the order of a few thousand, not a number which is itself has 1000 digits, but just on the order of 1000, and we can allow 1000 multiplications, of course, or maybe a few thousand. So what if e is not a power of 2? What then can we do? Let's consider a following example. So we already know how to compute powers of 2 of b modulo m. b squared, b to the 4th, b to the 8th, and so on. So how to compute b to the power of 13 modulo m then? Well, we can notice that 13 can be represented as sum of several powers of 2. Because we know that any number can be rewritten in its binary form, and so any number can be represented as a sum of the powers of 2. And then b to the power of 13 is just product of b to the power of 8 times b to the power of 4 times b to the power of 1. So this is the idea of how we can actually compute b to the power of 13, although 13 is not a power of 2 itself. So in this example, we represent e as a sum of powers of 2, and then we compute this table of b to the power of 1, b to the power of 2, b to the power of 4, b to the power of 8, all the powers of 2 which are less than or equal to 13. We do this with the squaring algorithm from the previous, and we know all these remainders are correspondingly 7, 5, 3, and 9, and then we only need to multiply some of these remainders. In this case, we need to multiply the remainders for b to the power of 1, b to the power of 4, and b to the power of 8, which is 7 times 3 times 9. 7 times 3 is 21, which gives a remainder 10 modulo 11, and then 10 times 9 gives a remainder 2 modulo 11, and then in the end we conclude that b to the 13 modulo m is equal to 2. So what we do in this case is we rewrite e in binary form. We compute b to the power of 2 to the power of k modulo m for all powers of 2 which are less than or equal to e. And then we multiply together the results for all powers of 2 in the binary representation of e. So first we spend binary logarithm of e multiplications to compute all the b to the powers of 2 which are less than e, and then additionally at most binary logarithm of e multiplications to compute b to the power of e modulo m itself by multiplying all the needed b to the 2 to the kth modulo m for all to the kth which are in the binary representation of e. So in total we will do at most 2 times binary logarithm of e multiplications. And to conclude, modular exponentiation can be computed using at most 2 binary logarithms of e multiplications instead of just e multiplications. And for numbers e which have thousands of digits, this is just a few thousand instead of a huge number with 1000 digits itself. To do that, we represent e in binary form. We compute b to the 2 to the power of k for all powers of 2 less than or equal to e using squaring, and then compute finally b to the power of e modulo m as a product of all needed b to the 2 to the power of k using binary representation of e. And in the next videos we are going to study the useful properties of modular exponentiation operation, which allow us to safely encrypt and know that Eve probably won't be able to decrypt our cipher in any reasonable time.